Hi everyone, welcome to our first lecture on set theory, say unit 1 of algebra. Again, I'm your tutor, Miss Egan. That's why I prefer to be called. Alright, so let's look at what we have under set theory. We'll have 6 things to go through, but in this video I'm going to take that of the first 4. I think the first 4 should do. So I'll take the basics, right, notations, to the types, and in the second video we'll take that of the operations and then the Venn diagram, and in all we'll look at some problem solving. Okay, so let's move to the basics of set theory. There's a recap of what we've done in the basic schools, or let me say in the high schools. And now if you look at this image here, it says a set and there are some items in it. We can say there's a collection of fruits, and so there's one keyword here: collections of something or gathering of something. I also have collection of, I could say, outfits. Yeah. Now in all these two images you see a peculiar thing. They are distinct collection of fruits or the words, and so I have the word distinct. Now these objects are also referred to as elements. So the fruits, the dresses are elements. So this element becomes my fruits and then my dresses. Is how to spell dresses here. And these are also objects. They are distinct objects. This means we don't expect any repetitions in the collection. So if you already have a banana, there shouldn't be another banana in your collection. Other than that, it refuses to be a set. So that is just the basics of set theory. Let's look at the representations. How do we represent sets? There are various forms of brackets in our daily mathematical representations. You can see the first one is a curly bracket. Let me use a different ink here. The second one is a square bracket. The third one is we call it parenthesis. Forgive if you can't see the spellings or the writing. And then this is the angle bracket. For the set theory, we use this very first one, please. So I have here as required. We use a curly bracket, not the square, not the parenthesis, not the angle. And so in this curly bracket, we'll have our elements or our object contained in it as you see it here. Not the square. So I can have object 1, object 2, object 3, object 4 through to the end object. Another interesting thing about these representations is that the objects are separated by commas. So you see comma here, comma here, comma here. Please, it is not full stop, object 2, full stop, object 3, full stop, or colon. No. Or semicolon. Semicolon is dot and then this. A dot and then a comma. No. It is also not using a backslash. No. So you take note of the various representations for me. Let me use the red ink too. Not a full stop, not a colon, not a semicolon, and not a backslash, or there's a backslash. We don't use this one, we use the commas. So if you write the object or the element and then you use anything aside a comma, it refuses to be a set. So we don't really care whether you even use a curly bracket and then the objects are 1.2. No, there's no set. And if you use a square bracket and then I have 1.2, this is still not a set, even though you've used a comma here. So you kindly take note of the representation for us. All right. Now let's look at the notations. There are common notations in set theory, from union to intersections to being a member. This is also called a member in other textbook. That is an element, a subset, proper subset. All these are common notations we'll encounter in our set theory, so I wouldn't waste much time on them. We'll get to use them in the course of the lectures. Let me move to the last thing for the lecture video, that is the types of sets. Now if you look at my slide, I have various types of sets. Sets. How many do I have here? 1 2 3 4 5 6 7 8 9 10 11. I have 11 types of sets here. If my counting is right, that is what I have. We'll go through each of these in pairs to make it simple for us to understand, instead of taking one after the other. The pairing makes you appreciate the differences, so please flow with me. Let's look at the first type, an empty or the singleton set. I always love to use images to describe things, and our brains are very good in capturing images. Like watching movie, you can remember the scenes, but if it's in writings we hardly remember. So look at the image here. Why is the first one a singleton set and why is the second one an empty set? It means that a singleton set has just one element. So I have here only one element, please. And then the empty is a no element. So we have a jug with we are expecting to have collection of let me say fishes in it, not the water. Someone will say, but there's water in the jug. No, we want to look at collection of fishes. And in the first jug we have one fish, type of fish. In the second jug there's no fish in the water. Okay, we use the notation either the empty curly bracket or this to represent an empty set. Again, an empty set is also called a null set, so you take note of that for me. That is a simple thing. If you have two elements, it is not singleton. You take note. The next step or the next kind of set is a finite and infinite set. Again, I have an image to describe it. Look at the first image. It is still a set because it's a collection of some item, distinct object, distinct element. There's no repetition and it is finite. Why? Because it is complete. It is countable or it is complete. Don't forget we have non-countable sets, which I wouldn't even get into it, but it's complete. Let me use the keyword here for safety reasons. And then for infinite, it is incomplete. It doesn't mean it is not countable. It is countable, but it is incomplete. It is not finite. So look at the example I have here. I have element 1, element 2. See what I used here. 3 dots, not more than 3. If you just write comma dot 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 dot, some of us do this. This is wrong. So please, anything aside 3 dot, it is wrong. And I have the last one, comma en, so the nth element. When I come to the second part, the incomplete, I have the 3 dots at the end. So this is in between and this is at the end to show that it's incomplete. But if there's something after the 3 dots, it means that it is finite, it is complete. So you take note for me. So look at our images again. The second one is incomplete because there's a natural numbers 0. There are so many of them. But the third image says it is an empty set. Why? Because the bracket is empty. there's nothing in the bucket. There's no fish, there's no apple, there's no number in the bucket, so that's an empty set. All right, the next step of the pairing, so I told the pairing is going to help us. We'll look at equal and equivalent set. Look at the word equal, equivalent. When we say something is equal, we already know there's equal sign here. If you don't know equal sign, yes, that's something else. And then there's equivalence notation, 3 strokes to show the equivalent. So you take note of the differences of the notation. Now equal means that the word is equal, so same element. Equivalent means the same number of elements. I have added another keyword, number, or someone will say count. Okay, so one is looking at the element in both sets, and one is looking at the number of elements in both sets. I have an inscription here, so if I'm looking at the number, they are not necessarily the same elements. Let's look at the example from slide 8. Why is the first one equal? I can match elements in one into the other. There's U, there's E, there's A, there's I. O is also seen in the other one. Is that all? A, E, O, I, E. Yeah. So I can match them, aside that there's no other element, so they are the same, even though they are arranged differently. In the equivalent set, they are not the same, but when I count them, I have the first one giving me 3, I have the second one giving me 3, and so they are equivalent because they have the same. 3 is equal to 3, so they are equivalent. Okay, before I say any other word, let's look at the question here. It says that equal set implies equivalent set, or the other way. Equivalent set means they are equal set. This can be very confusing because someone will come back to this and say 3 is equal to 3, so they are equal set. No. But equal set can be equivalent because they are the same. So look at the first example. I have A, O, I, what else? E, U. And then the second one has E, U, O, A, I. Even though they are arranged differently, if I count them, it is 5. If I count this, it is 5. Already they were equal sets. Okay, when I counted them, they became equivalent. So in a nutshell, equal set becomes equivalent set. But equivalent sets are not equal set because the elements are not the same. I have A, B, C, 1, 2, 3. They are not the same. So all equal sets are equivalent set, but the vice versa is never true. Take time and process this for me. All right, so I think I skipped one. The notation for equivalent, either I use the 3 strokes or I use the tilde. Okay, the next set of the set is a subset and proper subset. Again, look at the diagram very well. We use a symbol as I have already written here. One has a bar beneath it, the other has no bar. So we say contained in, or a member of something. That is for the subset. But proper subset says it doesn't have all the members, it has some. So look at the image. There's a group of stars with some colors. So A, B, C. C contains some of A. so it's proper subset. But B contains all of A, so it is a subset. Sometimes you might think proper subset because of the word proper, it means it must contain all because of the word proper, but please, it's not so. The proper is rather referring to you containing some of my elements. If you contain all my elements, you are my subsets. Okay. Now let's look at the other. I think there are two more to go. Disjoint and non-disjoint overlapping set. Disjoint, just as the word describes itself, they are separable. So let me add that term here. We are not joint. Okay, so I have certain words here. There's no intersection, there's no common element, there's no overlapping, and it means they are separate. If none of this thing is available, then it means you're looking at what? The non-disjoint set. Non-disjoint means there's intersection, there's a common element, there's an overlapping, they are not separable. There's something engaging them. So look at the image I have in slide 10. Is this ABC? Are they disjoint or non-disjoint? ABCs are disjoint because we can't have them. We don't see any common color. Let me write well. There's no common color seen in any of the A or B or C. In A or B or C, unless I'm colorblind. But there's no color in any of them which are the same, so it is a disjoint set. So I said images help us appreciate things. And then the last form of set is the universal set. Universal set. So look at my write-up in my notes. I have a big bag. I have some big bag. It contains certain things. So these things are what? The elements. I wouldn't say the element, but they are the sets. Yeah, they are the sets because elements are contained in sets. You realize I have a finite set in here. This bag contains a finite set because I have the 3 dots and then the last end set. And that is a universal set. It contains all the sets we are, all the sets we are working with. So like the image here, I have A, B, and C as different sets, all in A. So A becomes my universal set. B is a collection of fruits. C is a collection of fruits. A is a bigger bag containing B and then C. And so A becomes the universal set. And that is it for today. In the next video, we'll take the operations and then the Venn diagram and some word problem. See ya.